Dear delegates and invitees, and my dear friends, today we have parallel technical session number 6. It is my great pleasure to announce that in this parallel technical session 6, we have chair Professor H.N. Vasan sir from I.I.T. Roorkee and co-chair Dr. Shreyas V from GEM Foundation. And it is my pleasure to introduce the chair and co-chair. On behalf of the organizing committee, I'm extremely happy that Professor H.R. Vasan was former emeritus fellow and ex-professor and head Department of Earthquake Engineering, I.I.T. Roorkee, and former president of Indian Society of Earthquake Technology. He has teaching experience of 40 years and research and professional experience for over 45 years. He has successfully guided 6 PhD scholars and 26 MTech dissertation theses, and has published more than 85 research papers in reputed international journals and conferences. He has written one book and 2 book chapters. He has been awarded Life Fellowship of Indian Society of Earthquake Technology and a life membership of Indian Geotechnical Society and IGC specialization. His specializations include engineering seismology, seismic hazard and seismic assessment, risk assessment, seismic networks, regression relations, and pattern recognitions. He had the honor of being founder organizing chairman JM 2004 for all IITs and chairman JM 2005 for IIT Roorkee. Sir, I take this opportunity to welcome on this occasion and thank you for accepting our invitation to chair this afternoon session. I welcome you, sir, for this session. I would like to introduce our co-chair to the delegates, Dr. Shreyas V. Dr. Shreyas V has bachelor's degree in civil engineering and further specialized in the area of structural engineering. She defended her thesis in 2019 and obtained PhD from NITK Suratgal. Her PhD dissertation was on probabilistic seismic hazard assessment and site characterization of Southwest India. She continued her research career as a postdoctoral scholar at IIT Gandhinagar. Currently, she works as a seismic hazard modeler in GM Foundation located in Pavia, Italy. She has authored numerous journal articles and conference papers. She has delivered lectures on FDFIS conference and other I.I.Sc funded programs. Her area of interest includes structural and soil dynamics, earthquake engineering, and seismology. So with this brief introduction, I welcome the co-chair, Dr. Shreyas V, to conduct this session, madam.
Thank you.
Sir, I request the co-chair as well as chair I will hand over the session to conduct the sessions.
Okay. Thank you, Dr. Govinda Raju, for the nice introduction and giving details of this session. So, on behalf of Simon Ikraji, it gives me pleasure to welcome you all to this session, technical session 6. It gives me pleasure to have a special welcome to Professor Sebastiano Forti, who is the SOAP speaker at this session, and to other speakers and authors of the 6 technical presentations which are listed for this session. And also, I welcome all the attendees who have joined this session or who are likely to join this technical session for their interest in this topic. So before we begin, it is my honored duty to give a brief biodata of our SOAP speaker, Professor Sebastiano Forti. for the benefit of the young researchers. Professor S40 is a professor in geotechnical engineering and vice rector for education at Politecnico di Torino, where he also received his PhD degree. He has been chair for the civil engineering program from 2015 to 2018. He is a member of the technical committee TC203 earthquakes and a past core member of TC102 in situ tests. These committees are of ISS MGE. He is part of the project team for drafting the new version of Eurocode 7, Geotechnical Design, Part 2, Ground Investigation and Testing. His research activity is mainly devoted to geophysical methods for geotechnical characterization, with particular reference to surface wave testing, seismic waves in porous media, and the use of geophysical techniques in the lab. His other research interests include seismic site response, soil structure interaction, structural dynamic tests for the assessment of existing foundation systems. He has published over 180 papers in scientific journals and technical conferences, 3 books and 6 books chapters. He served in the editorial board of Soil and Foundation from 2015 to 2017. He was awarded the Geotechnical Research Medal, Bishop Medal 2003 by the Institution of Civil Engineers, United Kingdom for the best paper on geotechnical engineering, and an honorable mention in the best paper category in the Geophysical Journal in 2011 by the Society of Exploration Geophysics, USA. With this brief introduction, I now invite Professor S40 to deliver his SOAP talk. And the title of his talk is Uncertainties in Small Strain Damping Ratio Evaluation and Their Influence on Seismic Ground Response Analysis. So, Professor 40, please, now you take the floor.
Thank you, Mr. Chairman, and good morning, everybody. First of all, I would like to thank the organizing committee of the conference to invite me to deliver this lecture. Obviously, I would have been very glad to visit India, as I have a very good. I remember very well the last conference I was there with you in India, and it was a really positive scientific and human experience, but for this time we are going to deliver online. So the topic has been presented by the chairman. Let's see a brief, let's start with a brief outline of the topics. So I will briefly introduce the different uncertainties that we have in ground response analysis, and specifically then I will focus on the small strain damping ratio estimate, considering both the laboratory based estimates and the back analysis of the in situ measurements in downhole arrays. Then some hints from a case study, and finally some discussion of approaches that we can use to estimate directly on site the small strain damping ratio from geophysical tests. So let's start with a brief overview of the site of the uncertainty in seismic site response analysis. They are indeed a key aspect in seismic hazard assessment. However, we have several uncertainties, both on the side of modeling and on the side of determining the site parameters that have an influence on the site response itself. Therefore, it is of foremost important to have a way to handling these uncertainties, and this can be set up in a very consistent procedure. If we clearly identify the uncertainties, we manage to quantify them and to manage their influence on the final results. I will show you some results having this in mind. So a brief overview of the different uncertainties that we have, they are reported in this slide. Basically, we have uncertainties related to modeling. So the choice of the nonlinear approach that we can use for modeling, that can typically it is either an equivalent linear approach or a fully nonlinear approach. And this has a major influence as all the input parameters that we have to consider, that are the shear wave velocity profile, the modulus reduction and damping curves that describe soil nonlinearity, and the input motion that we use in the analysis, and finally two other parameters that sometimes they are overlooked, but they are also of most important. The shear strength of the material, that is especially important where we are dealing with deep and soft deposit, in which we, during the analysis, we may develop failure at a certain depth. And finally, the small strain damping ratio. We will see that this is last but not least during the presentation. As we are going to see, there is an important influence from this parameter too. Just in order to provide a few hints, I will say a few words about the shear wave velocity profile, and then I will leave all the other uncertainty except the small strain damping ratio. So I will describe in terms of uncertainty the shear wave velocity profile, and in this respect we can clarify that especially the role of this parameter, that is maybe the foremost important parameter. Indeed, it is the one that actually governs the wave propagation in the elastic medium itself. Typically, this parameter is estimated with in situ geophysical test. That is the best way to directly evaluate these parameters. We have a certain uncertainty. We can model uncertainty with several different approaches. The most common are the Toro model, that basically is a randomization procedure, and the APRI recommendation that basically are based on a lower and upper bound approach. And finally, there is a new geostatistical model that we recently proposed in 2020. And I will spend a few words about this model, as this is a new opportunity to model this uncertainty. Also, as the Toro model, also the model proposed by Passeri et al. Is a model for randomization, but it has some important differences. First of all, there is a clear separation of the uncertainty that we have on the two basic parameters that are space and time whenever we measure velocity. And these avoid to have parasitic uncertainties. So this means that we are able to generate realistic, always generate realistic models, and these realistic models are always in agreement with some specific site signatures, as for example the Rayleigh wave dispersion curve, rather than the experimental transfer function and so on. The model has been calibrated on a large database of surface wave tests, but it is very flexible. It can be adapted also to other kind of geophysical tests. And typically, the most important aspect is that it overcomes some important drawbacks in the fact that of previous approaches, in the fact that it always generates, as I said before, profiles that are online, that are compatible with experimental site signatures without overestimating the actual uncertainty that we have at the site. I will skip the description of the other uncertainties that we have. You can find the full description in the paper and also in my invited lecture at the ISEG conference in 2019, and I will now focus on the main aspect of the today's talk, that is the small strain damping ratio. So small strain damping ratio is typically estimated as a part of the characterization of the material in the lab. So when we characterize the material in terms of the nonlinear behavior of the material, we typically characterize the modulus reduction curve and also the damping curve that describes the variation of damping with strain, and specifically also the small strain damping ratio. In alternative, we can use empirical relationship that are in any case still based on laboratory tests. I will not describe in details the laboratory tests that are very well known in the scientific community, but I will just stress a few points of importance that introduce uncertainties in the specifically in the evaluation of the small strain damping ratio. So let's start from the dynamic test. So typically the resonant column, in which a sample is excited at different frequencies, and basically exploring the response of the sample at different frequency, we can derive its resonant frequency. And if we consider the theory of elastic wave propagation from this frequency response curve, that is the response of the sample at different, when excited at different frequency, we can also derive the damping ratio considering the aperture of this frequency response. Main problem with the resonant column estimate is that the soil is assumed to be linear viscoelastic, so the method is reliable only in the small strain range, but this is fine for us, as today we are talking about the small strain damping ratio. But the main problem with the small strain damping ratio is that typically there is an overestimate that is due to the equipment generated damping. So internally to the equipment, we have some level of energy dissipation. This is typically overimposed on top of the actual real estimation of the damping ratio of the material itself. So for example, here you can see in a study by Meng and Wicks the quantification of the estimation due to this effect. So which are the possible alternatives? One alternative is to consider the free decay that we have after we excite the sample itself. So after leaving the sample after stopping the excitation system, we will have a free decay of the vibration. In this way, we can study the free decay and avoid to have an influence from equipment generated damping. Other possible to estimate small strain damping ratio in the lab is cyclic test, so basically torsional shear test or the direct simple shear test, cyclic obviously. And in this case, we really study the response to cycle of excitation, and then by considering a cycle of unloading and reloading, we can estimate the dissipated energy. From this, we can derive the small strain damping ratio. Main problem in this case is due to uncertainties in the definition of the hysteresis loop, especially when we are at very small strain. So it's the objective of today's talk. Indeed, this at small strain, the hysteresis loop is not really well defined. As you can see, this causes a given variability of the estimate of the damping ratio if we consider different cycles of unloading and reloading. And finally, if we deal with the laboratory test, it is important to take into account the frequency dependence of the small strain damping ratio. Indeed, several studies have shown that whenever we estimate the small strain damping ratio with a resonant column, we have an estimate that is larger than the one that we obtain in cyclic test. This difference is basically related to the different frequency of excitation of the samples. Indeed, that high frequency, as those that are explored with the resonant column, we have different dynamic effect, and this leads to a overestimation of the damping ratio. So if we want to compare the two estimates, we have to correct for this frequency effect. For example, on this picture on the right-hand side, you see data after they are corrected for the frequency effect, and you see actually that indeed now there is a very good agreement between the resonant column and the torsional shear. So this is what is concerned laboratory tests that are typically used to estimate the small strain damping ratio. But now, if we go and see what actually happened on site, we can try to understand if the values that we obtain in the laboratory are actually always representative of the damping ratio that we can expect. So now, if we consider the back analysis of downhole arrays, this is if you wish, the most straightforward way to measure directly on site the damping ratio. Basically, what we do is we study the propagation of elastic wave on site, considering receivers at different depths. And from this set of data, we applying different possible approach, like the seismic waveform inversion rather than inversion based on the definition of the K0 parameters, or fitting the site amplification parameters, we can derive the small strain damping ratio. There are several applications of this approach in the literature. In principle, this is relatively straightforward, as I said before. We start with a given estimate of the shear wave velocity profile and then an estimate of the damping small strain damping ratio from laboratory test or from empirical relationship, and then we adjust the damping ratio profile in order to get a good fit with the empirical transfer function of the or a similar response parameters directly estimated on site on the basis of the downhole array data. In principle, this is straightforward, as I said, but in reality, there is a very large sensitivity to the amplification parameter that I actually use. For example, these are a few case histories reported by Tao and Raji in 2019. As you see, for different case histories, we always have that the small strain damping ratio that can be estimated is much larger than the value that typically we estimate in the lab. And another important aspect to observe is that the value that we get in terms of damping ratio is different depending on the fact that we consider the transfer function or the amplification function or an amplification in terms of peak ground acceleration and so on. So this means that there is a variability in the estimate. This is an important aspect. The second important aspect is that there is consistently an evidence of the fact that the damping ratio on site is much larger than one that we estimate in the lab. Main problem with the use of the back analysis of downhole arrays is that we need instrumented site, and obviously this is not always the case because we need to have instrumented site and we need to wait some time to record some meaningful events. The evidence in literature is in any case that the small strain damping ratio that we can estimate at the site is typically much larger than the one that we estimate in the lab, from up to 6 times the one that we estimate in the lab. The reason, is mainly due to wave scattering effect, especially when we have a complex stratigraphy, and to the fact that obviously our approximation of 1D propagation, is an oversimplification in most of the cases. So possible strategies are a direct modeling of scattering and 3D condition, but this is obviously very time-consuming and very costly. We can consider an indirect model of scattering in 1D simulation, and but in this, from this point of view, we need in some way to take into account the uncertainty that we have in the small strain damping ratio. So how to take this into account? There is an absence of a fully accepted procedure. In the remaining part of the lecture, we will make reference to the relationship proposed by the approach proposed by Stewart et al. That basically said we add on top of the estimate of the small strain damping ratio in the lab, we add an additional amount of damping that represent wave scattering. This additional damping can range from 0 to 5%. So we run a parametric analysis to take this variability into account. So let's see how this applies for a specific case study. So the example is taken from microzonation in Italy. If you want fully details of this, this is reported in our invited lecture in Reykjavik 2019. Rocca Fluvione site basically is as a profile in which we have some silty sands and then some silty gravel. And if we consider the results obtained with surface wave analysis with the MSW test, we see that at about 42 meters there is an interface with the bedrock below. So this is the shear wave velocity profile that we used as a reference. So again, in the paper in 2019, we explored the variability and the influence of uncertainties that we have in the shear wave velocity profile. As I said before, these uncertainties can be taken into account with the model proposed by Passeri et al. In 2020. We took into account the uncertainties in modulus reduction and damping curves to take into account a nonlinear effect, and we used the curve that were developed by Ciancimino et al. In 2019. And considering all these uncertainty, we ran several ground response analysis in order to estimate the variability that we can have in the results. Variability is represented here in terms of amplification function. So we have the median estimate of the amplification function, and we are able to quantify in some way the associated uncertainty, the associated variability. As I said before, we have to identify uncertainties, we have to quantify uncertainties, and this is done with this randomization process, and we have to manage the uncertainties in order to see which are the influence on the final results, in this case, the amplification function. Now, if we want to take into account also the role of the uncertainty on the small strain ratio, and if we follow the approach proposed by Stewart et al. In 2014, basically what we can do is to repeat the simulation here for the average shear wave velocity profile by considering just the small strain ratio that we have obtained for the lab, or increasing it either by 2.5% or to 5%. And now if we run the deterministic ground response analysis with these three hypotheses, what we get is something like this. So this is the influence that we can expect from our inability to estimate the actual value of the damping ratio on site. So this in blue is the estimate of the amplification function that we would have with the laboratory value of the small strain damping ratio. And obviously, when we add some additional damping to consider wave scattering, we will get lower result. Now it is interesting. So basically, this is the variability that we can expect due to uncertainties in the small strain ratio. Now it is interesting to compare this variability to the variability that, as I said before, we observed considering randomization of the shear wave velocity profile and randomization of the modulus reduction and damping curve. And this was the variability that we observed that was showed in the previous slide. So as you see, the variability associated to damping ratio can be even more important, or is in this example, is more important than the variability that we have from shear wave velocity profile and from the modulus reduction and damping error. So if we do not account for a proper estimate of the small strain damping ratio, we may seriously overestimate the response at the site. So for this reason, it is important to have methods to estimate directly on site the small strain damping ratio. This can be done with the geophysical test. Actually, this is something that is more on the research side, but we have to push in order to bring this to the state of the practice, because as we said, we have seen before, it is of foremost important to have a good estimate of the small strain damping ratio. So we have some promising method in geophysical test. I will briefly explore some of them. So considering boreal test, so either downhole or seismic CPT or cross-hole test, there are a few methods that were proposed in the past. I will just, for example, propose the method that was proposed by I.I.Sc in 2015, that basically is based on the spectral analysis of the wave that propagates whenever we run a cross-hole test with two receivers. So if we compare the signals at the first and second receiver, we can do a spectral analysis of this signal and basically observe that both the shear wave velocity and the damping are a function of the frequency, and considering the theory of of the linear viscoelasticity, and considering the Kramer-Kronig relationship, we can derive the small strain damping ratio as a function of frequency by fitting this expression. Other possible approaches are based on surface wave tests. Surface wave tests are becoming more and more used in seismic site characterization. This is related to the fact that they are quick and cost effective. The problem is that the interpretation is not so straightforward, but in order to provide you a reference, I put over here the guidelines that we recently developed and are published as open access in the Bulletin of Earthquake Engineering 2018, and just to have the general description of surface wave test and some guidance for good practice. The surface wave test can be also used to estimate the damping ratio. Indeed, if we analyze the attenuation of the surface wave, we can get some useful information in order to derive the small strain damping ratio. Over time, several different methods have been proposed to estimate the attenuation of Rayleigh waves as a function of frequency. Here you can find a list of some of the methods that have been proposed. Specifically, now I will speak of the transfer function method, of the wave decomposition method, that are very promising, and finally, one new method that we are actually developing at Politecnico di Torino. So, which is the basic concept, is that if we excite the soil with an active source, and then we record along a straight line the propagation of Rayleigh waves, we can study not only the dispersion, so not only the variation with the frequency of the phase velocity, but also the variation frequency of the amplitude. For example, in the transfer function method that was proposed by Rix et al. In 2001, basically what we do is that we consider the theoretical expression of the transfer function. We consider experimental data collected directly in terms of the variation of the transfer function as a function of frequency. And from this, we can, with a regression of the experimental data, we can obtain directly both the shear wave velocity profile and the attenuation of the Rayleigh wave dispersion and the attenuation of Rayleigh waves with a fully coupled process. So the advantage of this is that it's a fully coupled process. The advantage is that the cons is that it is reliable only with a single dominant mode. Then the procedure has been extended by myself in 2003, where using the concept of deconvolution, basically it is possible to use the same approach even when the source is not monitored. Another promising method has been recently proposed by Bergamo et al. This is the wave field decomposition method. The advantage of this method, again, also in this case, we have a decomposition of the full wave field, and again, considering a likelihood function, we can estimate the attenuation. The advantage is this method can handle multiple modes, so complex stratigraphy in which we have multiple modes of Rayleigh wave propagation. The problem is mainly related to the fact that it is a bit complex in terms of implementation. And finally, we recently have been working on a new approach that is based on the attenuation of the frequency wave number spectrum that can be obtained with a frequency domain beamformer approach. And this method has the advantage that has a very low computational effort and can obtain very good quality result. The problem is that in principle it is limited to a single dominant mode, but if we adopt it in conjunction with modal filtering, we can estimate the attenuation curve also for higher mode, not only for the fundamental mode. Just to provide briefly you an example of the results that we can obtain, these are data that have been collected with cooperation with Professor Brady Cox of the Utah State University, that formerly was at the University of Texas, Austin, and our data related to the characterization of the site of the Garner Valley downhole array. And from these experimental data that were collected both with a large electromechanical shaker and also with a sledgehammer in order to have a comparison, this is an example of how it is possible to extract very neat, very clean, not only dispersion curves of Rayleigh waves, but also attenuation curve of Rayleigh waves. And so, considering this set of experimental data, so considering dispersion and attenuation of Rayleigh waves, then we can solve an inverse problem aimed at estimating not only the shear wave velocity profile, but also the damping ratio profile. A very important aspect on this is that not only we estimated the best fitting profile, but we have also an estimate of the uncertainty associated to the best fitting profile. And we can use this quantification of the uncertainty in order to manage the uncertainty itself. So some final remarks. Identification, quantification, and management of uncertainty is of foremost importance for any engineering application, but specifically for dynamic nonlinear problems like the one that we face in seismic design, because an a priori choice of conservative values is not possible. We know that for static problems, we can have a priori choice of conservative values, not for dynamic problems. So we have to manage the uncertainties that we have. Specifically, the effect of uncertainty in the small strain damping of the ground is as relevant as the uncertainty that we have in determination of the shear wave velocity profile and the uncertainty that we have in modulus reduction and damping curves. We have seen this in one example. And typically, approaches for estimating the small strain damping ratio rely on laboratory tests, but we have some underestimation because we do not account for scattering mechanism that we have on site. On the other side, using downhole arrays is very cost and time consuming, and promising approaches for the estimate of the small strain damping ratio comes from geophysical methods and specifically from surface wave test, because we can obtain reliable estimation, and also especially we can also evaluate the associated uncertainties, considering the uncertainties in the solution of the inverse problem. With this, I thank you for your attention, and I take the occasion to thank my two co-authors that are Mauro Aimar and Andrea Ciancimino. Both of them are PhD students at Politecnico di Torino, and I owe to them the preparation of both I mean, a big help in the preparation of both the paper and this presentation. So thank you again, and I leave the floor for possible question and answer.
Thank you, Professor Forti, for a very interesting and informative lecture on a very important problem of uncertainties. And it has been demonstrated by you through lab and in situ tests and the lab tests that consideration of effects of uncertainties is very, very relevant, and it should not be ignored. They have to be considered. So thank you very much for a very, very interesting and educative presentations. Maybe that we can take the question answer session at the end of all the presentations, and I hope you will be available till the end of the session, so we can now move on to the technical papers presentation. There are 6 technical papers listed for this session. The first 2 technical papers, one on seismic hazard and risk assessment in Maharashtra, a critical review, and the second one, damage assessment of tunnels in seismic prone zone during earthquakes, a part of hazard evaluation, are by Dr. Abdullah Ansari from IIT Delhi, India. So may I request Dr. Abdullah Ansari to present both these technical papers in sequence, and then at the end of the session we can take up the question answers session. Over to Abdullah.
So myself, Abdullah Ansari, I'm a PhD researcher at IIT Delhi, working with Professor Rao and Jan. My today's topic is seismic hazard and risk assessment in Maharashtra, a critical review. This is the review paper which discusses about the different methods that we use to study the seismic hazard and what studies has been done in Maharashtra. So this is the overall flow of my presentation, which includes introduction, earthquake in Maharashtra, seismic hazard assessment, liquefaction hazard assessment, geophysical testing, and conclusion. So, every day we listen about the news related to natural hazard, maybe earthquake, tsunami, or volcano. So if we talk about the Indian subcontinent, then we have the collision of Indian plate and Eurasian plate. So we have Himalayan formation in the north, and we have subduction zone in the south part, like this Andaman part. So this map is from the BIS, Bureau of Indian Standard, which divides India into different seismic zones, like 2nd, 3rd, 4th, and 5th, based on seismic intensity. So Maharashtra falls under zone 3 and zone 4, we can say zone 3rd or 4th. So it comes under like moderate to high seismic risk. If we see the past earthquakes that have been happened in Maharashtra, so the most famous is the Koyna 1997 earthquake, 1967 earthquake, and the 1993 Latur earthquake. These are the most devastating earthquake happened on the land of Maharashtra till date. So for earthquake hazard or hazard study, the first thing is the seismic hazard assessment. So seismic hazard assessment is like nothing but a likelihood of experiencing a specified intensity and damaging phenomena at a particular site. So we have 2 approaches here, like deterministic approach and another is probabilistic approach. So deterministic approach is completely based on maximum credible earthquake, and in which we don't consider any uncertainties like temporal uncertainties or spectral uncertainties. While in case of the probabilistic seismic hazard assessment, we consider uncertainties which is involved, like temporal or spectral. So these are the steps given for both deterministic seismic hazard assessment, and another is your probabilistic seismic hazard assessment. In case of DSHA, we first identify the sources, then we calculate minimum source to site distance, and we predict the controlling earthquake, that is the giving the maximum value of the magnitude, and then at the finally we use different attenuation relationship to calculate either PGA or PGB. But in case of the probabilistic seismic hazard assessment, Of course, we consider the seismic sources, but we involve the uncertainties like temporal uncertainties and spectral uncertainties. And for the same, we have to go through some attenuation relationship. But yeah, here we form the earthquake recurrence interval model. And at the end, we develop hazard costs like mean annual rate of exceedance for different probability like 2%, 5%, etc. So this is the approach based on seismic hazard assessment. So this is the result for Mumbai city given by Desai and Chaudhary 2014. This is nothing but the peak ground acceleration at bedrock, not the spectral acceleration. And this is calculated for 50th percentile and 84th percentile. So here we can see that the south part of the Mumbai city, which is very near to the coast or Arabian Sea, we can say, this is like more susceptible to earthquake. And here we can observe the peak ground acceleration up to 0.5, 0.6 in the regions like Panvel and Kolaba. So the next approach to study earthquake hazard is liquefaction hazard assessment. Liquefaction hazard assessment is mostly defined using a factor called liquefaction potential index, which is calculated by means of integrating factor of safety at a particular soil column. And this definitely help us in microzonation and further town planning and to understand the vulnerability of earthquake motion in a particular area. Liquefaction hazard assessment is done for different return period like 475, 1000, 2000. Then this is a map given for two different magnitudes like 6 magnitude and 7 magnitude for the same return period 2475 years. Yeah. The last approach that I am going to cover in the current presentation is geophysical testing. So this is completely based related to the shear wave velocity, and we know that shear wave velocity is a parameter which helps to understand the dynamic properties of the soil. And to estimate shear wave velocity, we have different approaches like SASW, MSW, CPT, etc. But here, this is shown for MSW, multi-channel analysis of surface waves. And it's a completely field-oriented method in which first we calculate the phase velocity, then after the dispersion analysis and inversion analysis, we recorrelate time domain and frequency domain, which use as shear wave velocity. So this is the map given for Nanded city, which is one of the district in Maharashtra, and this shows the shear wave velocity distribution across the city. And here we can see that the northeastern part and of course the southern part of the city is showing the higher values of shear wave velocity here, and your eastern part is having shear wave velocity ranging between 200 to 300, which can be seen here. Based on the value of the shear wave velocity, we divide the area into different zones based on NHERP guidelines like class A, class B, class C, class D. And in case if we are falling in class A and class B, like rocky strata or very hard rocky strata, then yeah, of course, the site will be safe for any future construction work. So this is the overall summary and conclusion that what we learned from the current presentation, that Maharashtra before 1993 and 1967 we used to consider a stable continental region, but these the earthquakes that have shown that yeah, a stable continental region can also face the earthquakes because this is the part of entraplate earthquakes. And what are the approaches? So DSHA, PSHA is the approach, and DSHA is a quick process and which is based on maximum credible earthquake like maximum magnitude, while PSHA is the over and above your which covers the drawbacks of DSHA and consider uncertainties which is involved in the hazard estimation like type of earthquake sources, physical processes, magnitude scaling, recurrence model, etc. And yeah, MSW is the easiest method to estimate shear wave velocity, and shear wave velocity helps to understand the dynamic properties of soil. And these all factors in a single basket helps in seismic microzonation. So this is the oral presentation. These are the references referred in the presentation as well as paper. Yeah, thank you so much for this presentation.
Well, you may now continue to your next paper. So we'll take up the questions at the end.
Sure, sir. This presentation discusses about the damage assessment of tunnels, especially in the mountainous region. and which is subjected to earthquake. Like if we talk about India, then the state Jammu and Kashmir and northeastern states have the same like mountainous terrain, and of course subjected to seismic hazard and earthquake ground motion. So this is overall flow for this presentation, like panel damages due to earthquake, like how to grading damage and indexing, damage assessment model, and the we modified assessment model, so called modified damage assessment model, and the conclusion. So if we talk about the earthquake hazard effects or the ground motion effects. So liquefaction, landslide, of course, tsunami, these are the effects of earthquakes, but we observe these effects on the surface. But what happens inside the earth? So what are the effects for underground structures or substructures? So these are the pictures from damaged tunnels due to past earthquakes. So this is from the Daiki station in Japan, which is damaged due to Kobe 1995 earthquake. And these two tunnels are from China, which is damaged during 2008 Wenchuan earthquake. So it was a complete catastrophic event having magnitude 8.0. So in this event, like we observed lots of damage to the tunnels, underground structures, pipelines, etc. So they have given some guidelines related to damage grading and damage indexing, like when we can observe the tunnel or any underground structure can get damaged. So for that, they have given some guidelines, like if you are having ground motion less than 0.19 G or 0.2 G, then you will not observe any damage for the rocky tunnel in the rocky strata. But if in case if you were having the PGA, peak acceleration ranging between zero point 0.2 to zero point 0.5, then yeah, of course, you can observe minor damage here. But in case if your PGA is greater than 0.5 G, so you will observe the like major damage. So in case if we talk about the India and seismic recognition map of India, so Jammu and Kashmir falls in zone 4 and zone 5. So zone 5 maximum 0.36. So there we can observe damage in case if any earthquake activity occurs. So here I have divided damage into different zones, like based on the texture or pattern of the damage. So in case if there is very small cracks or very small cracks and damage, so we can say no damage class. And in case of the minor rockfall, then we can say minor damage. And in case if we observe that destructive cracks at the portals or at the lining, then we can say moderate damage. But in case if you observe like fall of big rocks on the ground surface, sinking of road surfaces that we observed in the initial slide during the Daiki station of the Japan damage due to Kobe 1995 earthquake. So this can be put in the severe damage class. And the last one is your collapse. Collapse is the complete damage of your tunnel, and this may be the like most worst condition of damage. And here you need to reconstruct the whole structure, and the traffic, etc., can be interrupted. So for developing damage assessment model, we have taken the data from two past earthquake, 1995 Kobe earthquake and 1999 Taiwan Chichi earthquake. Like both have damaged the tunnel. So we have directly got the data of the material data for these two past earthquakes in terms of earthquake intensity, rock classification, tunnel length, overburden depth, and we also consider that either any fault is passing through these tunnels or not. So we have considered the data from the tunnels damaged during the 1995 and 1999 Taiwan earthquake. So based on rocks, we have further classified into two categories, either the rock is soft or hard. And similarly for magnitude, we considered different classes, like 4 classes based on magnitude 7, 8, 9, and 10. And overburden depth, you can see that it's varying from 4.2 very small to very like deeper earthquake, like 350. Mostly for deeper tunnels, it is assumed that it will not be get damaged, but we, of course, we consider to understand the damage assessment model here. And we use the least square method of regression analysis to calculate the factors or coefficient for this damage index. And here we can see this J represents your number of factors. Here we consider 5 factors, And K represents a factor that we consider. It is completely like related to linear pseudo y equal to ax plus b. So we have taken like two motor views like A and B, and based on the probability we select any motor view that like which will be like suitable in case if any damage happens in a particular area. So after these five factors, we added have taken two more like fortification strain and portal stability. Like some parts of the tunnel get damaged for the like old construction, like tunnels constructed before 1990 already like weak, so we have put them into a different class like no fortification, and then 7, 8, 9, 10 with the different magnitude of the earthquake, like different classification. And yeah, of course portal stability, so we have further classified into four, like very bad, bad, good, and very good based on the available data. So this is the another model for the damage assessment. And here we can observe the calculated value of the coefficient and the suggested value of the coefficient. So suggested here represents for the seismic damage assessment model considering 7 factors, while calculated considered for only 5 factors. So this is the conclusion about the current presentation, that what we did damage assessment modeling considering 5 and then 7 factors and data collected from 1995 Kobe earthquake and 1993 earthquake. And this will definitely help in further design of the channel considering seismic loading conditions. And there are of course some other major factors which are not considered in this study, but we can also encounter those factors to modify our existing damage formula, and it will help in mitigation measures with the early warning system as a part of hazard evaluation, which will lead to less damage of channel properties. So these are references used to collect the data for the two earthquake 95 and Taiwan. And this thank you so much.
Okay.
Thank you. Yeah.
Thank you, Mr. Ansari. Now we will move to the next presentation by Dr. Naveen James from I.I.T. Roorkee. His topic is site characterization using satellite data and estimation of seismic hazard at ground surface. So please.
Yeah, thank you. Thank you, Professor Watson. Thank you, Shansvi, Professor Govindaraju. Very good morning, good afternoon to everyone. So my topic is site characterization and estimation of hazard using satellite data and the estimation of seismic hazard at the ground surface. So these are the contents of my presentation. I'll directly go to the introduction part. So now it is pretty clear from my previous speakers, like the Indian subcontinent is prone to earthquake hazards, which have been evident by the NDMA. They already stated that around 59% of Indian landmass is prone to the earthquake risk, and the damages and the casualty caused by the earthquake in the past 20 years is huge. And we can mainly highlight it to the lack of proper preparedness against the earthquake. So underrated design, and so the tremendous growth in the urban population, rapid urbanization, and underrated construction technique, and land use and the non-standard land use techniques made most of our cities and urban centers vulnerable to earthquakes. So as one of the previous speakers said, so one of the way out is to start with a seismic zonation. So first you have to quantify the hazards in the region and classify it according to the various levels of hazard, do a zonation based on the different levels of earthquake hazards. And the steps includes in the seismic hazard zonation starts with a seismic hazard analysis. So where we get the peak horizontal acceleration and spectral acceleration, details about the maximum credible earthquakes and hazard curves. Then we go into the seismic site characterization, where we try to map the subsurface profile, estimating the rock depth, then determine the site classes based on the average shear wave velocity of top 30 meter. And then we perform, I'm sorry, actually there is one more thing, is there's a site amplification hazard, which I missed, I'm sorry. So then we have to carry out a site amplification. We have to determine the site amplification local site effect, where we do ground response analysis, linear, non-linear, equivalent linear, whatever suitable. Ground response analysis, and determine the hazard at the surface level. And then we have liquefaction hazards. So where we generate the liquefaction maps, hazard map, factor of safety map, and also liquefaction probability map. Then all these hazards, along with the hazard influencing parameter, has to be clubbed and form an integrated hazard map, which can be either which is a microzonation map. It can be deterministic or probabilistic in nature. So in this study, I just concentrate on the seismic site characterization part. So here we use the satellite data. So as already the previous speaker said, that we need dynamic soil properties, basically shear wave velocity, to characterize the site. So yes, there are different methodologies available. We can do it based on the local geology, which is very crude, and then the geotechnical field test and geophysical field test data. And basically, we are I'm going to present is the site characterization based on the topographic slope. So just a brief review. So based on local geology, it is very approximate, less reliable, and it doesn't capture the variation of shear wave velocity within a geological unit as well. So mainly it is more suitable for a macro level, for a very large study area and all. But the site characterization based on geotechnical and geophysical test, even though there are the speakers have clearly mentioned about the field test and the lab test as well. So there are to do it for a very large area requires a very large resources, and it is not possible to do it physically for a very large region like a state like Karnataka, or for the entire country like India. Now here is when we have a topographic slope based site characterization comes into the picture. Now with the evolution of digital elevation model, GIS, and remote sensing, we do have the digital elevation model for the entire world. Basically, these two are the typical the DEM database, digital elevation database, that is the SRTM, and the ASTER database. There are other databases are also available, which are having much more resolution. So in this study, we have took the SRTM data for the India, so for characterizing the entire India, and the SRTM based DEM for the site characterization of the Karnataka. And they have been converted into UTM coordinate system. So they are just GIS operations, and they are resampled into 5 kilometer by 5 kilometer and 10 kilometer by 10 kilometer grid size. So this is the digital elevation model of India. And then we generate from using ArcGIS, we generate the slope map of the two study areas. Now the site characterization technique. So typically, the studies by Vlad and Allen 2007 has proposed that the topographic slopes or the near surface geomorphology can be a proxy for the shear wave velocity. So we can say that the steep mountains represents a rocky terrain, much more harder, and flat basins represents the soil, and the intermediate slopes is the transition from the rock to soil. So based on that, they have conducted a study, and they have correlated for various the slope ranges, and they correlated to different slide classes, which is already available. And we have used it, and then we have created the site class map. Okay, so this is the typically slope map, and this is the site map of the Karnataka, and the site class, the spatial distribution of site classes for India. Now, for site amplification hazard assessment, we first carried out deterministic and probabilistic hazard analysis. I'm not going to go in detail because the previous speaker has already given details about it. But here we, for carrying out the site amplification hazard, we used a nonlinear site amplification technique proposed by Raghukant Iyengar, for which if we know the bedrock level acceleration, we just have to multiply with the factor, the amplification factor, to get the site hazard at the surface. And the amplification factor is a regression relationship. For estimating the amplification factor, the regression relationship has already been proposed by Raghukant Iyengar for various site classes. So we have taken that, and then this shows the typical variation of the what they call peak horizontal acceleration across the at the surface level throughout the state of Karnataka and India. And this is for 475-year return period for both study areas. So now I conclude. So yeah, so the major conclusion is, yeah, so yes, the accurate way of estimating the site classes or doing a site characterization is based on geotechnical and geophysical test or laboratory testing. But if you want to do a first level of assessment for a very large area in order to identify vulnerable zones, the geotechnical and geophysical test-based approach is not viable, because it requires sample collection. It requires a very large resources. So at first level, if you want to identify the vulnerable regions and all, the topographic study, the site characterization based on the topographic slope map is very ideal. And it can be, we can carry out the hazard analysis using, we can carry out the site characterization with a moderate degree of reliability. And once we identify the hazardous zone, then a detailed study can be carried out based on a geotechnical method and geophysical method and laboratory testing to capture the exact non-linearities and the uncertainties in the site class assessment, the site characterization. Thank you. This is a very short presentation. Thank you. I'm sure I'm well within my time.
Yeah, thank you, Dr. Naveen. Thank you for a very interesting lecture showing the use of satellite data for seismic hazard and site characterization. Now I invite the next speaker, Mr. Mohammed Ahmed from Building and Road Research Institute, University of Khartoum, and his topic is site-specific seismic ground response analysis for typical soil sites in central Khartoum, Sudan. So, Mr. Mohammed Ahmed, please.
Thank you. So, although Sudan lies in an intraplate region, which is seismically stable, we have some active regions near the Red Sea in the eastern state here at the Gulf of the Red Sea, and also in the southern part of Sudan. But there is some recent activated fault near Khartoum in a range of 100 kilometers in the year of 2010, 2013, and 2014. We have performed preliminary evaluation for earthquake-induced soil liquefaction in our previous study, incorporating a probabilistic SPT-based procedure, and we found that the probability of liquefaction with a minimal effects. So in this study, we further quantify the local side effects from two soil sites in central Khartoum here at the meeting of the Blue Nile and the White Nile. And central Khartoum is underlined by a loose to medium dense low plastic sandy material locally known as Jazeera Formation. So we have used the equivalent linear procedure as it did not require the kind of expertise. This is the two models we used for side 1 and side 2, and the average profile used for the liquefaction analysis. Also, for the dynamic soil properties and some other soil properties like unique weight are not available for some parts. We have assumed that the unit weights like for clay material is about 18 point something, and for dense to medium sand is like a range of 19 to 20 kilonewton per meter square. Also, the water table it's almost ranging from 4 meter to 8 meter. For the input earthquake motions, the Sudanese seismological network started in 2010, and unfortunately, the record, I mean, in the year of 2009, the after the section of the Sudan to the two parts, Sudan and South Sudan, the network. The network have been brought to the southern part, so we do not have record for earthquakes. We have used for earthquake from Eritrea, like Kub earthquake, Nasser Ridge earthquake, and Numa Prieta earthquake, but we apply a scale to this earthquake to a factor of 0.1 G, which is from the seismic hazard assessment of Sudan done in 2001 by Jamal et al. For the dynamic soil properties, we calculate the shear wave velocity using the closed form, the empirical closed form formula, and also the deep soil software calculate the shear wave velocity. And as you can see that the difference, the relative difference is quite minimal. The result, we will present the result for the surface acceleration time history and the response spectral and amplification factor due to the time constraint of this presentation. We get a maximum acceleration ranging from 0.17 G to 0.25, correspondingly amplification ratio of about 1.7 to 2.5 G respectively. For the response spectrum, we get values ranging from 0.3 G to 0.13 G at a period of around 0.4 second, which is in a similar range to period of structure in Khartoum, and we have recommended that this facts must be considered in our structural design. As there is no seismic code or any provision against earthquake loading here in Khartoum. For the Fourier amplitude, we found that Fourier amplitude ranging from 0.55 to 0.83 at frequency in range of 2.5 to 1.9. So for the conclusion, as it's well known that the lure of soil sites is well known in many earthquakes, but here in our study we did this to primarily quantify the capability of our local soil sites in the presence of earthquakes. For the deep soil software, we recommended that the deep soil software is reliable and quite good in estimating the dynamic soil property, such as the natural period. For a big ground acceleration, we found big ground acceleration ranging from 0.17 to 0.25. For the response spectrum at the 0.5 damping ratio found to be ranging from 0.68 to 1.34. And also for the Fourier amplitude found to be ranging from 0.43 to 0.85. And the message here is that the input motion as well as the characteristics of the input motion itself and the and the soil and spatial variability all play important role in shaping the amplifications and also other for complete understanding of ground response analysis. Thank you.
Thank you.
Thank you. Thank you, Mr. Mohammed Ahmed, for presenting an interesting case study. Now I invite the next speaker, Mr. I.I.Sc Agarwal from ACSIR CBRI Roorkee. His talk has a topic, stochastic response surface-based probabilistic analysis of geosynthetic reinforced soil slope under pseudostatic conditions. Mr. I.I.Sc, please.
A very good afternoon to all of you. I'm here to present my research work on the topic stochastic response surface-based probabilistic analysis of geosynthetic reinforced soil slope under pseudostatic conditions. Co-authors are Dr. Anindya Pine and Dr. Shantanu Sarkar. The introduction, the outline goes like this. First of all, I'll talk about slope instability, then design of reinforced soil retaining structures, followed by a literature review, methodology, results, and then the inferences. Now, 1 second. First of all, slope instability. In the slide, there are several reasons listed for the slope instability, like erosion, rainfall, earthquakes, geological features, etc. However, in the present study, we will talk about the remedial measures concerning with the reinforced soil retaining structures. Now, the design of reinforced structures. It can be done by many methods. There are analytical methods, numerical methods, experimental methods, and there are many technical reports and manuals available, like Federal Highway Administration. The two main approaches of analytical design are deterministic and probabilistic. Now, the deterministic method, it increases the factor of safety to make the design somewhat safe, which may result in the increased cost of construction, and it neglects the uncertainty in the geotechnical parameters. The probabilistic method is contrary to the deterministic method. It takes into consideration the uncertainty of input parameters, and it is somewhat accurate, efficient, and it may be more economical than the deterministic methods. Talking about the literature review is divided into 3 parts. First, about the deterministic methods. Second, about the probabilistic methods, which include first order reliability method, Monte Carlo simulation, second order reliability method, excluding the surrogate modeling methods. And the third section is about the surrogate modeling, which include the stochastic response surface methods. Now, the deterministic analysis. It involves the use of limit analysis or limit equilibrium method. In the present study, limit equilibrium method of horizontal slice method is used. The horizontal slice method was proposed by Liu and Zhou, and it has been used by many researchers such as Shagoli et al. And Nouri. The 2n+1 formulation of horizontal slice method is used. In this formulation, the vertical equilibrium for each slice and the horizontal equilibrium for whole wedge is satisfied. The geometry of the log spiral failure mechanism and the slice and the forces acting on a particular slice are shown in the figure. Stochastic response surface method. Now, stochastic response surface method is just an extension for the traditional response surface method. It creates a meta model or a surrogate model of the original deterministic algorithm. Why is it so? Because the original deterministic algorithm is not computationally cheap. It is computationally inefficient. So it creates a surrogate model of the original deterministic algorithm, and then the Monte Carlo simulation or any other simulation is performed on that surrogate model. In general, Hermite polynomial chaos expansion is used for the approximation, and the PC of third order is used in the present study. The equation for the expansion is shown here. Another equation is for the number of terms in the expanded form of third order Hermite polynomial chaos expansion, in which n is the number of random variables. In the present study, the number of random variables is 3, and hence the number of terms comes to be 20. To ease out the process of solving regression-based stochastic collocation method, the stochastic collocation method is used to calculate the unknown coefficients. The equation to calculate the number of collocation points is shown at the end of the slide. Now, this slide shows the probabilistic framework for reliability-based design of the geosynthetic reinforced slope. First of all, we define the input random variables and their distribution. In the present study, we have 3 random variables and we define their distribution. The second one, then we proceed to the realization of the collocation points. The collocation points is chosen at the roots of the next higher order polynomial. Like in the present study, we are using the third order polynomial chaos expansion. So we will choose the roots at the 4th order. Then the calculation of performance function is done and a stochastic response surface is obtained, followed by the Monte Carlo simulation on that computationally cheap stochastic response surface. Talking about the results, first of all, we will do the validation of the deterministic results. The deterministic result validation is done with the Nouri et al. 2006 for the input parameters shown in the slide. As we can see, I have done the comparison for 2 values of KH, 0 and 0.15. However, the results are excellently matching with Nouri et al. For all other values of KH. And we can see that the value of required K is the normalized required tensile strength of the reinforcement. It is decreasing with the increasing value of phi. Now, to check the accuracy of the collocation-based stochastic response surface method, regression analysis is performed for 2 slope angles, for 50 degree and 60 degree. And we can see from the graph that the value of coefficient of determination is greater than 0.95. It is 0.99 for both the cases, for 50 degree as well as for 60 degree. This shows that the collocation-based stochastic response surface method is very accurate and efficient too. Coming to the results section, we have taken 3 random input variables. One is the soil unit weight, another one is the internal friction angle of soil, and third one is the ultimate tensile strength of the reinforcement. The value of internal friction angle of soil is chosen as 35 degree because this is a cohesionless soil, and the coefficient of variation of this parameter is varied from 5 to 15%. Why? Because it is the most influential parameter. The distribution is also shown on the rightmost column of the table. The graph beneath the table shows the variation of probability of failure and the reliability index with the coefficient of variation of phi. We can see that as the uncertainty increases, the probability of failure also increases and the reliability decreases. However, the probability of failure for slope angle 50 degree is less than 60 degree. The values required to obtain this graph are also shown in the table beneath the graph. Talking about the inferences, it is very simple to infer that the simple 2n+1 formulation of HSM is very efficient and accurate in calculating the values of performance functions. A third order PC is acceptable for performing the CSRS, collocation-based stochastic response surface method, with a very high efficiency. And while performing this, the limit state function is evaluated 125 times. We have used 3 random variables, so 5 raised to the power 3 comes to be 125 times. So the performance function is evaluated 125 times in CSRS method, while this performance function is evaluated 50,000 times, or we can expect more in MCS. So one can judge that how efficient this method is. If we talk about the time, then the stochastic response surface method takes 10 minutes and MCS takes about 14 hours for the same simulation with same accuracy. The coefficient of variation of phi, as seen from the previous slide and the graph, has a great influence on the stability of slope. An increase in coefficient of variation or uncertainty leads to a substantial increment in the value of probability of failure and hence in the decrement of the reliability index. Heartily thank you for your patience, and any questions are welcome. Thank you so much. These are the references.
Thank you, I.I.Sc. I think the questions will be asked after we complete another presentation.
Yes. Okay.
Okay. Thank you, Mr. I.I.Sc. for an interesting results. Now we move to the last speaker of this session, Mr. A. Mukesh. The title of his talk is Local Site Effects Influence on Earthquake Early Warning Parameters. So, Mr. Mukesh.
Good afternoon, sir. So first of all, I would thank for all professors for giving such kind opportunity to give my oral presentation in a prestigious conference. Thank you so much. Myself, Mukesh, I'm a research scholar from Center of Excellence in Disaster Mitigation and Management from I.I.T. Roorkee, under the supervision of Professor Ravishankar Jakka and Professor Kamal, in the collaboration of Aquatic Engineering Department and Earth Science Department. My topic is here, it's totally a different field, a different uniqueness compared to all other things, because here we are focusing on the early warning parameters, which influenced by local site effects. We did some kind of studies to analyze whether the influence is there or not by using the site characteristics parameters. So these are my upcoming contents: introduction about the aquatic early warning parameters and its principle and methodologies, how it is working, and what are the warning parameters which I consider for my work, and how it is influencing by site effects, and the data collection where I made. Then its results and discussion can be categorized into two categories. One is the site classification, and another one is whatever I found the parameter, I compared those things with the function of magnitude and epicentral distance and the shear wave velocity, and its conclusion, then references. So this is the introduction term. Generally, we all know about the earthquake early warning. It is just some kind of prior information before the earthquake. Here it is give the clear statement. The term earthquake early warning is used to describe a real-time earthquake information system. Here you will see the overall representation of the earthquake early warning process. The brown line, the slanting brown line, that is represent the fault line rupture, and the cylindrical box here, it is represented that the front detection alarm, that is regional alarm. It is a site-based alarm. In upcoming slide I will explain this thing. And it is why it is saying the real-time earthquake information system, because it is collecting the real-time data through the internet or through the telecommunication services. So it is called a real-time earthquake information, and it is provide a potential warning. Why it is? Because compared to the seismic wave, the electromagnetic observation is very speed. So based on the system, we will get the data. Next, this is possible by rapidly detecting the ground motion radiating from the earthquake rupture and estimating the ground motion prediction equation based on the data. Then the warning times, because the warning will be given in the few seconds of the origin of the earthquake. So here we consider the few seconds warning period. So it is based on primarily a function of distance of the user from the epicenter where the earthquake has been originated. So these are the principle and methodologies, how the processing has been done inside the earthquake early warning. Generally, based on the installation of sensors, here we can classify the two types of earthquake early warning system. One is on-site and another is regional. On-site is nothing but where we are targeted to give the warning. That particular site we call the on-site. So there we will install a single sensor, and based on the data we will provide the information. But in regional approach, it is a group of network. That means seismic network. We have so many stations. There we can get the data, and we collected the data, and we can transfer through the telecommunication through some other main station. Then we will give the prior information. Here you will differentiate in two categories. The sensor is installed at the same place where the warning is issued. Here the sensor is placed near the epicentral site. That means it is called as a regional site. Then what are the parameters I consider? There are so many early warning parameters, but this two parameters is the robustic parameter. At commercially, it is in the field of research, ongoing process. So tau-C method and PD method. Tau-C is nothing but the average characteristic period of the motion from the fault zone. So why we are focusing that initial, the period parameter means generally the fault, don't know. Only the period, the initial motion of the period, which is representing the fault. That means still the fault is growing or not. So that's why the tau-C plays an important role to calculate this kind of information. So generally the tau-C has been formulated by Nakamura 1988 and Wu et al 2005. He modified some kind of data. Generally the first thing, it is the ratio. That means this characteristic period will basically derived from the Parseval theorem. Parseval theorem is nothing but it is a energy conversion between the time and the frequency spectrum. So here the formulation has been derived from the formula. That means the tau-C equal to 2 pi root of r or it is termed as the ratio of integral of square root of the velocity amplitude and ratio of integral of the displacement amplitude. Based on that, we will calculate the that means velocity and displacement ratio. Then here we consider the 3-second motion. According to the previous author suggestion, we follow the same second of motion, because the 3-second will give the upcoming information of the shear wave or whether the event is very strong or not. So here this 3-second will decide that. Then the second one is PD method, that is a peak displacement amplitude method. It is a robust measurement. Why it is robust measurement means it's directly considered the motion parameter without including any kind of uncertainties. Directly we can take the motion amplitude and we can calculate the magnitude based on the parameter. So these are the data collection. I collected the data from the Japanese strong motion database from KeekNet. So here I consider the 7 site, that means 7 stations, their data, that latitude and longitude and the epicenter. Here I am focusing the near epicentral region up to 70 kilometer. I covered the station. How the parameter is influencing by the soil. Then this is the signal characteristics which I consider. Generally in strong motion database, Japanese strong motion database, they have a KeekNet, KeyNet. There are so many seismic data websites. Here I am focusing KeekNet. Why I am focusing means it have the borehole sensor as well as the surface sensor also. So we can directly get the borehole motion also, surface motion also through the installed sensor. We can directly collect through the website. So these are the some example I am showing. The red one indicates the borehole motion. You can see the amplitude is lesser amplitude with the function of time. Then the second one is surface motion, which I collected this motion in a particular site. For the showcase purpose, I will show here. Then generally the sensor observed motion have a many kind of noises and it is being uncorrected also. So for that we need to correct the signal characteristics. So signal characteristic, here I am focusing the P wave. P wave, why I am P wave using the P wave means it gives the prior information, because we consider the initial motion. Initial motion is always transferred into the P wave, primary wave motion, as we all know that, compared to the S wave. And I am choosing a vertical component because the seismograph or any accelerometer, they have the 3-component motion. Why I am choosing the vertical component? Because P wave energy is very high compared to the another 2-component motion, because those 2 components have the shear wave dominant motion. Here it is a primary wave dominant motion. That's why I'm choosing a primary wave after the recorded data. Then for the filtering of the noise, I am choosing a filter type is Butterworth filter. Or Butterworth filter, it gives the narrow frequency band without no ripples. And the filter configuration, here I am using band pass, because why I am using band pass, the earthquake signal is categorized into some kind of lowest frequency range to highest frequency range. So the cutoff frequency, here I am focusing the lowest level is 0.075 Hz. And the maximum cutoff frequency, here I am focusing on 30 Hz. In between, the motion frequency is considered as the earthquake frequency as per the seismology view we know. So the parameter I calculated from the bedrock and the surface motion, because I got the surface borehole sensor data also, surface data. So I compared those things, how the parameter is changing with respect to the medium, with respect to the soil. Here for local site effects, generally in this two graphical pictorial, it will represent the function of magnitude and the function of epicentral distance, how the period has been varying compared to the bedrock and the surface. You can see the orange highlighted one is the surface parameter and the blue highlighted is the bedrock parameter. So in all the sites, the characteristic period is increased in the surface parameter compared to the bedrock parameter. So it clearly represents there is some kind of uncertainties and some kind of amplification will take place through the soil and the medium properties with the function of magnitude. And here also this pictorial representation gives the parameter is increasing. That means the tau c is increasing with function of the epicentral distance is also increasing. But with irrespective of the epicentral distance, the bedrock and the surface motion is also the surface motion parameter is also increasing. There are two kind of uncertainties we found. So for that, we need to study a lot of studies to justifying this relationship. And this is the variation of peak displacement amplitude with respect to the magnitude. That everything it is showing a negative downward direction. Why means compared to the by the kicknet sites, those are the very stiffer site classification. So in the surface there is not that much level amplification. Only the bedrock side is showing the amplitude level. The surface it is showing little stiffer than the bedrock. So that's the reason here we are getting the logarithmic displacement is very low. That means negative direction because the motion is a very minimum amplitude. And
Mukesh, you need to
the third one is the site classification. Local site effects has been characterized into two. There are so many kind of studies are being there based on the topographical effect, based on the site effect. Site effects will be categorized into soil effects or basin effects. There are so many factors. So here I am focusing on the soil factors. Primarily, I took the soil factor characterized by the stiffer. That means stiffness. Stiffness is represented by the shear wave velocity. So the sites which I collected based on the National Earthquake Hazard Research Program guidelines, I classified the site. Here, the one site it is come under the part of very soft type, the site class D. The remaining all sites C, it is showing a stiffer compared to the site class D. You can see the surface magnitude with respect to the average shear wave velocity. The site within the range of 200 to the 400, the amplification of the early warning parameter is very high. Once the site shear wave velocity is increasing, the amplification of the early warning parameter is decreasing. What it is representing means by softer site, the amplification of the parameter is very high compared to the stiffer site. So whenever the stiffness is increasing, the motion, that means average characteristic period of the early warning parameter is increasing. By increasing the depth, it is decreasing. Then the second is variation of the PD, that means peak displacement amplitude with the average shear wave velocity of the site. Here also you can see the site which undercome the 200 to 400 range, it is showing the higher value compared to the remaining sites, because those sites which falls into the site class C, it is considered as a stiffer. That means whenever the medium stiffness is increasing, the characteristic period or the logarithmic displacement amplitude is also decreasing. But whenever the stiffness of the medium is decreasing, the amplification of the parameter it will show very high. So these are my conclusion I made. Generally, the earthquake early warning parameter here we found the tau C and PD of the surface motion is observed high. That means for the surface motion is high compared to the bedrock motion, with increasing the size of the earthquake for the considered sites. What it is representing, it is clearly represents that the size of the magnitude is increasing. The early warning parameter, which I consider peak displacement amplitude, and the period is also increasing. So one thing is proof. Then the second is similarly the tau C parameter is increasing with respect to the epicentral distance. It is a generalized observation I made in the particular representation. Then in the same representation, the increasing of tau C in the surface motion compared to the bedrock motion with an irrespective of the epicentral distance. For this relationship, we want to do the further many studies to justify this relationship between the early warning parameter with the function of epicentral distance. Then the sites which under the category of soft soil type, class D,
please now conclude.
190 to 360. Observe that the surface motion early warning parameter shows higher as compared to the bedrock motion. It reflects that the sites which are the soft soil type, it shows the higher amplification. So for finalized, we want to do the many further studies to justifying those relationships. It is a initiated work in our India. It recently a upcoming era. The work is deals in the upcoming era also. So we started this work and we got some kind of site effects influence in those parameters also. For that we did some kind of analysis. Then I showed those results. So thank you very much.
Okay, thank you, Mr. Mukesh, for the interesting results. Now we will have question and answer section, and I will request Dr. Sreshvi to organize this, and we will go in the same order of presentation, starting with the SOAP and onwards. Please.
Oh, okay, thank you, sir. So the first session we had was a lecture by Professor Sebastian Foti. So Dr. H.S. Mandal has asked a couple of questions in the Q&A. The first question is there any correlation between shear wave velocity and damping ratio?
Okay, so there is at large a correlation, in meaning that softer materials tend to have a larger damping, but it is a correlation that cannot be, quantitatively cannot be taken as a reliable correlation. As a matter of fact, the two quantities are strictly related, as during the presentation also highlighted, on the basis of the linear viscoelasticity theory, because there is the causality principle that makes them one dependent over the other. But if we talk about empirical correlation, it is not reliable to correlate empirically the two quantities.
Okay. There is another question, probably it was during the slides that you were mentioning. What do you mean the amplification factor value 2.0 at low period and less than AF 2.0 at higher period?
That depends strictly on the characteristic of the site, because multiple amplification at different frequencies, they are related to the site stratigraphy, and we may have conditions in which the first amplification period is the amplitude of the fundamental frequency is less than the amplitude of higher frequencies. This is especially when we are dealing with very small strains, where the damping is limited, and therefore the stratigraphic amplification due to change in shear wave velocity may lead to such kind of condition. This typically happens whenever we have, for example, sites in which we have velocity inversion, so we may have a stiffer layer that is close to the ground surface and then the bedrock that is deeper. So in such condition, we may have this kind of fissure. Typically, when we move to larger strain, then the damping increases and this effect cannot be observed.
Okay. And lastly, sir, I have a question myself. So when you were talking about uncertainty in VS profile, so there were a couple of methods you said. One is by the Toro model and the one is EPRI recommendation and so on and so forth. So whenever we are considering multiple VS profiles, are we addressing the spatial variability of the VS or the uncertainty carried due to the measurement type? For example, we do...
Okay.
Yeah.
Yes, typically, this is a larger topic of epistemic rather than spatial, epistemic uncertainty rather than spatial variability. This is not, an easy question, meaning that in principle we can divide these two kinds of variabilities, but as a matter of fact, in most cases, it is not that easy to separate the two kinds of uncertainties. And for this reason, in principle, also the Toro model is aimed at study the epistemic epistemic uncertainty, but as a matter of fact, if you go deep into the methods, you understand that is rather a variability from site to site. So it is difficult to. In the method that we developed, that is the method proposed by Passeri, that was a PhD student here at Polytechnic di Torino. In the method that we developed with Federico Passeri, and you can find in a paper in Soil Dynamics Earthquake Engineering 2020. Basically, what we aimed to was to get an estimate of the combined uncertainty related to both effects. But one very important issue, in my personal opinion, is that many times both the Toro model and the APRI method, they lose the connection with site signature. So they lose the connection with the actual site, because you have a variability that is much larger than the real variability that you can expect. You create with these kind of approaches unrealistic profiles that then may drive your estimate, your final estimate of the site response to completely wrong results. So I really recommend you to have a look at this new method that we developed that always keep realistic soil profile.
Thank you. Thank you. I'll definitely take a look at it. So I think that was all for you. So thank you for taking time
and
answering the questions. Yeah. So next, we will move on to the first presentation, which we had. I'm sorry, if you're online, please switch on your camera. I guess the presenter is not there actually. Okay, I will move to the next, the third presentation, which was by Naveen James. And
yeah, I'm here. Yeah, thank you.
Yeah, I think there is one question: how well the outcome of VS study profile generated from the slope studies compares with the geophysical studies? Is the model needs to be calibrated for a specific area being studied?
I guess if you are talking about the what do you call, the site characterization using topographic slope and the site characterization using the geotechnical and geophysical tests, as I've said, it is the geotechnical geophysical tests are very accurate. The topographic slope map capture so there is a variation in the topography, then only we can capture the site characteristics or site classes for that region. So we have not in the study, the another study we have carried out a comparison. We have carried out a comparison between the topography, the site class maps generated from the topographic slopes and with that of field data for Bangalore and for Chennai. So it is not matching exact to exact, but you can say that the entire region, if I divide the entire study area into the north region, south region, east region, and west region. So briefly, it can show that overall region in the west comes under the site class B, which is similar to that has been found, that has been determined using the field test or geotechnical and geophysical test. The other side, most of the study area on the one part comes in site class C, so that has been reflected. So for a macro level, yeah, it gives an fairly reasonable estimate. But for a small study area, just like we are looking at a nuclear power plant site or very critical installation sites and all, then then the site characterization based on topographic slope map may not be advisable. We have to go for a rigorous method. So this is for a larger area and for a primary level of study, to carry out a initial assessment of the hazard or carrying out zonation. This technique would be ideal. I hope I answered.
Even I had a question on similar lines, and probably answered it partially. Because I think the correlation developed by Allen and Wald was for the data that they took from US and Japan.
Yes, California, basically based on California data.
So, should we worry about the applicability in the Indian condition, or does it carry certain amount of uncertainty when we are trying to adopt
obviously there is a large uncertainty, but we have, as I've said, we have done comparison study for Bangalore and Chennai, Madras. So we found that both the maps are relatively okay. We have not quantified the exact uncertainty, but when we are doing hazards microzonation for a larger area, our objective is to identify patches of hazardous regions. Let's say for in India, we know, obviously, for a seismic hazard point of view, the Northeast and the Himalayan region are very much vulnerable because we expect large amount of PGA there. But when we look at the site amplification and liquefaction hazard point of view, the Indo-Gangetic plains are vulnerable, where there are alluvium deposits are there, so which can amplify, deep soil deposits are there, which can amplify the ground motion. So our method will identify these locations. Okay, these are the major chunks of regions are there, which are very hazardous, which need a careful planning. So once we have a macro level zonation is available, then we can look at those specific sites. Okay, these sites, let's say Indo-Gangetic plain. Okay, now there we expect large amount of site amplification and liquefaction hazard. So there we cannot go with a normal model, where we have to do an in situ analysis, because liquefaction and the site response are highly non-linear, depend upon the soil, and that is non-linear, its dependency is non-linear, as Professor Sebastiano Forti has already said. So we can see there is a high uncertainty there. So there we cannot go with a topographic slope, and there we have to do a precise experimental study to do that. But only thing with the experimental study, we should understand, it is difficult to get those samples. Professor Sebastiano may agree with me, because preparing those sample, mounting in a resonant column, keeping those, getting those undisturbed sample, especially in sands, are very difficult. So that should be, those kind of analysis may be reserved for the critical installations where the demand is so much. So that is the main highlight that I want to put forward through my presentation.
Okay, thank you.
Yeah,
so the next presentation, what we had was from Mohammed Ahmed. Please unmute yourself if you're online. Hello, yeah. As far as I can see, there are no questions specific to your presentation, but I had just a small suggestion. It was not clear to me, or maybe I missed it, how VS profile was obtained, and maybe a little more conclusion was needed in your presentation. It's just a suggestion.
No, we have used an empirical correlation with the standard penetration in value. But yeah.
Yeah, in the end, I just felt that maybe a little more clarity on the conclusion aspect, because I think you were talking about the Sudan city. So it would have been nice or interesting to see where we are seeing maximum amplification, where you are seeing a lesser amplification, if at all, if you had a wider coverage of data. That it's just a suggestion for you.
Yeah. Okay.
Yeah. Thank you.
Thank you.
Our next presentation was by Ekansh Agarwal. So there is a question for your presentation. You have chosen long normal distribution for phi parameter. State the reason.
Thank you for the question. The main reason for choosing internal friction angle of soil, phi, as log normal parameter, because this is a parameter which cannot be negative in the simulation. Now you must be thinking that gamma and tensile strength of the reinforcement can also be they also cannot be negative. But when we formulate an algorithm, then phi is taken in radians, and there is some chance that it slips to the negative side of the axis. That's why the distribution of phi is chosen as log normal. We can see this also when we choose the coefficient of seismic acceleration, horizontal seismic acceleration or vertical seismic acceleration. We choose their distribution as log normal or exponential, not normal, because the value of kh is so small that it can by accidentally slip to the negative side when we increase the coefficient of variation. So to avoid these circumstances, I have chosen the distribution of phi as log normal, and other two are chosen as normal. Thank you so much.
And I just have a small suggestion. In the conclusion, it would always be better to highlight what is a specific contribution from your study, and also a little more clarity about the data that you're using, or what exactly you're trying to achieve through the study in the beginning, or the objective of your study or something like that. That should give us more clarity to the audience.
Sure, ma'am. Sure, ma'am. I'll definitely take this up in my next presentation. I'll keep it in mind. Thank you so much for your suggestion.
Thank you. Yeah. So the last presentation was by Mukesh A on earthquake early warning system.
Yes, ma'am.
Actually, there are no questions for your presentation, but I have one. So you
Okay,
have
ma'am.
chosen the lower cutoff frequency is 0.076 hertz. So on what basis did you choose the lower cutoff frequency?
Ma'am, actually, I choose a cutoff frequency based on the reference paper like Umin et al. And Nakamura 1988. There they suggested the noise level, the minimum noise level can be characterized in the 0 point. That means it's not a standard. There are so many ranges, but they suggested 0.075 hertz as a for their results. It gave the good accuracy, so I follow the same thing. But they defined that it is a minimum noise level cutoff frequency. It is a range I choose like.
Okay. So have they used the same
If
KNet data?
Ma'am, I'm not getting.
Have they used the same KNet data?
Yeah.
For
That means
coming-
side data is different, but the motion, whatever they consider the component, vertical component, I consider the same.
Okay, because
I have
we're
a-
talking about.
I have a question, if time permits and you permit.
Yes, sir. Yes, sir. That's pleasure for me.
Just
Thank you, sir.
yeah, just a minute. I'll just summarize my question.
Okay.
So next, because we had very less number of stations, it could be beneficial for you to calculate a signal to noise ratio for your entire waveform. You can take the first 20 seconds as the noise window or something, depending upon how your waveform actually looks, and then you calculate the ratio, and then I think it would be better because, as you said, it is not specific to a site and it could vary. So it would be better to make it more specific to your study and also for your recordings and for your site.
Yeah, ma'am. Yeah, because the thing is, it's not like a standard accuracy based. We cannot talk on that because there are so many uncertainties. It is like finding of the parameter influencing the side effects influencing, because we cannot standardize whether this parameter based on this parameter it is changing or not. We cannot define it. So I am trying all other side characteristics, because here we attempt the study, just it's not for a full research based. We attempt a study for a particular site, how the influence being there or not. So for that we concluded, okay, there is some kind of influence based on the side effects, because previous algorithm, it doesn't have any side effect. That early warning empirical algorithm is there for the warning thing. So there they consider the source and the path effect. There is no side effects. So for that purpose, we need to improve the accuracy of the warning period prior to the earthquake. For that, we need to include the site data in the empirical relationship. So for that, we are working. My work is related to that. So that's why. Yes.
Vasan sir, it's up to you.
My question is that do these local site effects have a role to play in flagging a early warning based on few sensors close to the epicentral zone?
Yeah, sir, actually I previously explained this, because here we attempted the study, initiated the study for how the influence has been there, and mainly as like Dr. Shreyashi ma'am, I explained also, still in our India and the abroad also, there is no any kind of accuracy information for the empirical relationship which included in this earthquake early warning system. So in India, we started around 2011. For that, we are working actually. So we are trying to develop such kind of effects, side effects, to include in the previous empirical relationship.
Okay, Dr. Shreyashi, you may conclude. Thanks the speaker and conclude.
Thank you, sir. Thank you very much, sir. Thank you, ma'am.
Yeah, Mukesh, next time please finish it on time, because everybody is usually on the clock.
Okay, ma'am. It's not visible actually my side. That's the problem.
Shall I speak?
Please.
Hello?
Yes.
I would like to know the affiliation of Mukesh. Mukesh?
Research
Hello,
scholar,
sir.
I think.
Mukesh is a research scholar in CODM IIT Roorkee.
Okay, sir. Fine.
After monitoring the corrective actions from the corrective action.
Okay. So if Govindraju sir permits, I would conclude this session.
So we have completed all the presentations, including SOAP lectures. It is a wonderful session, what I observed when compared to the morning session. And I found it very interactive. And the chair and co-chair have raised critical comments on that, which would be really an eye-opener and then beneficial to our younger researchers or even for practicing engineers. Sir, on behalf of the organizing committee and on my behalf, I thank the chair of today's session, Professor H.R. Vasan, and then co-chair Dr. Shreyasi for chairing the session here. In spite of your busy schedule, accepting our invitation and make it possible to happen in our parallel session. I take this opportunity to thank the SOAP lecture by Professor Sebastiano Portillo for his wonderful presentation and thought-provoking lecture, which will be inspiring to everybody. I also thank the presenters Abdullah Ansari, Naveen James, Mohammad Hamad, and Elgam Agarwal, and then Mukesh for their very interesting and thought-provoking lectures on the state-of-the-art practices, particularly in seismic hazard analysis. I thank once again one and all for making this session a lively one. Thank you, sir and madam, for your kind information. We have a scheme to give best paper presentation award only for student category.
Okay.
So I want you to discuss and propose a name to me so that I can take it forward to the organizing committee so that the prizes will be distributed in the validatory function. So please, sir, Vasan sir, and then madam, you please.
Well, I will ask Dr. Shreyasi to suggest the name, because in the beginning I had asked her to evaluate these presentations, and in the end we will discuss.
Yeah.
So she.
You can propose a name there here only in the chat box. So nice to see you, sir. Thank you very much, sir.
Thank
Once
you
again.
very much. Okay.
Yeah.
Thank you, madam. So,
bye, madam.
Okay.